late 1915, Einstein completed his masterpiece, a new theory of gravitation called general relativity. At this point, Einstein was already a legend in the world of physics. However, he went back to work in the problem that fascinated him the most, light. And he did it again. In a few months, he discovered a deep connection between Planck's blackbody radiation and Bohr's atomic model that set the basis for the laser and served as a guiding principle that led to Heisenberg's matrix mechanics. This is the story of one of the most important and underrated discoveries in quantum physics, involving matrices and probabilities. And yes, this is a work done by Einstein. Contrary to popular belief, Einstein was totally fine with probabilistic quantum physics. This result became very significant in the early stages of the theory of quantum mechanics developed by Werner Heisenberg, but also had a significant technological impact. Let me remind you that in the year 1900, Max Planck solved the mystery of radiation emanating from hot objects by using a math trick. 5 years later, Einstein proposed that Planck's trick was in fact a true feature of nature, and that light does come in quanta that today we call photons. 2 years later, Einstein and Peter Debye used the same idea to solve the mystery of the specific heat of solids. And in early 1909, Einstein discovered that Planck's distribution hides a surprise. Radiation has wave and particle properties. Between this and 1916, the main remarkable discovery in the description of light and matter interactions was Bohr's atomic model. Planck, Einstein, and Bohr unveiled 3 secrets of the quantum world. However, up to this point, all quantum rules did not come from a single quantum theory, but rather a collection of clever guessing and close interaction between theory and experiments. During 1916, Einstein attempted to connect Bohr's idea of interpreting light from materials as electrons jumping between quantized energy states with Planck's blackbody radiation formula. These two seemingly unrelated phenomena had one thing in common. The energy of the radiation is exchanged with atoms in the material in discrete amounts. According to Einstein, since this exchange of energy between atoms and light leads to precise experimental signatures, understanding this emission and absorption of energy should guide the physics community to a complete quantum theory. Einstein decided to tackle the problem, but found an obstacle. Bohr's description leads to Wien's radiation distribution, which is only a high-frequency limit of Planck's radiation law. But then, in a remarkable insight, he solved the issue and proved the consistency of Bohr's idea with Planck's approach. Let me show you the details. Before calculating anything, let me outline Einstein's train of thought. The goal is to derive Planck's law from Bohr's idea. Einstein imagined a cavity filled with radiation and atoms exchanging energy. Then he calculated the probability of each interaction between the atoms and light. Then the equilibrium between radiation and atoms gives an equation whose solution should give the energy density of the radiation. Of course, Einstein knew the answer. The radiation energy density must be Planck's radiation law, which was experimentally verified in late 1900. However, the challenge was to derive it from first principles and evaluate its consistency with Bohr's model. Einstein began with a box containing a gas of molecules or atoms, represented here by the circles. They interact with a radiation field, represented by the arrows. Following Bohr, he introduces the idea that the possible states of the atoms only exist in discrete levels. Inside this box, there are 2 ways by which atoms and radiation can exchange energy. Excited atoms can spontaneously decay to a lower energy state by emitting light, and light can be absorbed, leaving the atom in a higher energy state. The atoms can have many energy levels. Here we have only 2 arbitrary energy levels that I call Ej and Ek, with Ej greater than Ek. Einstein called them epsilon n and epsilon m, but I will use Jk here, of course. Let's now denote the total number of atoms by n and the number of atoms in a given state, say state j, by n sub j. We can now use the definition of probability to calculate the probability of an atom to be in the state j as this ratio. Assuming a Boltzmann distribution, this probability can be written in terms of the energy of the state and the temperature inside the box, where P sub j is a statistical weight in case many states can have the same energy. This is called degeneracy, and I introduced it in my video about Sommerfeld's work extending Bohr's atomic model. From this definition, we can write the number of atoms in a given state like this, which we will need later. Now we characterize each of the two processes inside the box. Spontaneous emission occurs when an excited atom decays to a lower energy state by emitting radiation. The rate at which this process occurs is proportional to the number of excited atoms, because the more excited atoms we have, the more likely that this process can occur. Einstein wrote the rate of spontaneous emission in this way, where A is a proportionality constant and the minus sign indicates that when this process takes place, the number of excited atoms decreases. Incidentally, this is the same equation used to describe radioactive decay. The indices Jk denote that the atom transitions from the state J to the state K. Note that with this interaction, the atoms give energy to the radiation in the box. Absorption is the reverse process, in which the atom borrows energy from the radiation and transitions from the low energy state K to the higher energy state J. The rate at which this process occurs is proportional to the number of atoms in the state K, but also to the energy density of radiation, so that the rate of absorption is given by this expression, where B is a new proportionality constant. The indices Kj in B denote that the atom transitions from the state K to the state J. Now we can write the total transition rate as the sum of these two terms and impose dynamical equilibrium by setting this equal to 0. This means that the number of atoms in the state J remains constant. Each atom that decays by spontaneously emitting radiation is compensated by another atom that absorbs energy from the radiation field. That is the meaning of setting this quantity to 0. By replacing the expression above, we can easily solve for the radiation density ρ. Now we use the formula for the number of atoms in each state found earlier, which gives us this expression. If you watched my video about how Planck solved the mystery of blackbody radiation, this expression should look familiar. In case it isn't, let me make the following choices for the overall factor and the energy difference. Plugging this back, we get Wien's radiation law. Recall that Wien found this formula after years of work guided by experiments. Now Einstein rediscovered it only with a few assumptions and a very simple calculation. Nonetheless, Wien's law is only a special case of the general formula discovered by Planck. Einstein was clearly on the right track here, but something was missing. He struggled with this, while at the same time he was exploring the consequences of his theory of general relativity. After discovering that his equations predict gravitational waves, he returned to his atoms and light in a box, until he had one of those ingenious ideas that made him Einstein. On August 11th, 1916, he wrote a letter to his dear friend Michele Besso. Dear Michele, a splendid light has dawned on me about the absorption and emission of radiation. Einstein proposed that in addition to spontaneous emission and absorption, maybe there exists a third type of interaction making atoms and radiation exchange energy. In this new process, an excited atom is influenced by the radiation to decay into a lower energy state by emitting radiation in addition to the original photon. This process is now called stimulated emission. The rate at which this process occurs is proportional to the number of atoms in the high energy state J, but also to the energy density of the radiation ρ, so that the rate is given by this expression, where Bjk is a new proportionality constant and the indices denote that the atom transitions from the state J to the state K. And now we simply repeat the procedure followed before. we write the total transition rate as the sum of all these terms, impose dynamical equilibrium, replace the expressions above, and solve for the radiation density ρ. Using our formula for the number of atoms in each energy level, we get this. At this point, Einstein makes an assumption. He assumes that for infinitely high temperatures, the radiation density diverges, which leads to a relationship between the B coefficients, and simplify the radiation density to an expression that looks very similar to Planck's law. This assumption, by the way, is quite justified. This is just another way to impose the Rayleigh-Jeans formula valid at high temperatures, which Einstein knew was correct from classical mechanics. It is here that Einstein proposes that the ratio of the A and B coefficients and the energy difference are given by these expressions, from where he rediscovered Planck's radiation law. It is important to recognize what Einstein achieved here. Only using that energy levels are discrete and introducing a new interaction between atoms and radiation, he found that Planck's and Bohr's ideas are mutually consistent. In his letter to Bezo, Einstein called it a stunningly simple derivation of Planck's formula, I might say the derivation. I should mention that this is only half of the article. The other half is not less relevant, in which he studied the mechanical details of the energy exchange between atoms and light. It is here that he wrote for the very first time that light of frequency nu has momentum h nu over c. Although this relation can easily be obtained from his relativistic formula for energy as well as from his study of momentum fluctuations from 1909, this is the first time that it is explicitly demonstrated that when light interacts with matter, the momentum h nu over c cannot be ignored, because it is as important as the energy exchange. This is exactly the advice that Arthur Holly Compton followed when he demonstrated that in X-ray scattering, light must be treated as a particle and not as a wave. During this last identification, Einstein also justified Bohr's frequency condition, which is fundamental in Bohr's atomic model and until now was just a conjecture. Einstein was forced to postulate a new process for the emission of radiation and also to make the prediction that the ratio between the coefficients characterizing spontaneous and stimulated emission must satisfy this relation. This prediction is very important, and I will get back to this in a minute. Note that Einstein had no way to calculate each of these coefficients. He believed that this task would be possible in the future with a complete theory of quantum physics. Einstein concluded that a new process for the emission of radiation should be possible. However, it was unclear how to experimentally test this prediction. Note that in the process of stimulated emission, each photon gets duplicated because the incoming photon produces two photons. This process had tremendous technological potential for the amplification of light. It took several decades for Einstein's theoretical idea to become practical, which included many technical challenges and the development of new concepts like population inversion and the need for more than two energy levels. The first functioning device using these principles was built by Charles Townes and his team at Columbia University in 1953. They used the stimulated emission in ammonia molecules to amplify microwaves and call it the maser, an acronym for microwave amplification by stimulated emission of radiation. A similar device was created in the Soviet Union by Nikolai Basov and Alexander Prokhorov. The three shared the Nobel Prize in Physics in 1964. Exploring shorter wavelengths, Townes and his students proposed the so-called optical maser. Since the amplified radiation was in the visible part of the spectrum, the optical maser was later renamed laser. In 1960, Theodore Maiman in the US built the first functioning laser. Today, lasers are found everywhere, from crucial applications in industry, manufacturing, communications, and medical procedures, to daily uses in printers, barcode readers, and one of the best cat toys. Today, the quantities A and B are called Einstein coefficients. Mathematically, Einstein introduced them as proportionality constants to write the rate of each process, but physically they represent the transition probability from one state to another. This idea of considering different states and quantifying the probability of transitioning from one state to another is well known for mathematicians studying so-called stochastic processes, and the object used to represent these transition probabilities is a matrix, a transition matrix. Note that A and B characterize the strength of each process between atoms and radiation, and from the beginning, Einstein defined them according to the law of probabilities. Moreover, he ends his 1917 paper explicitly indicating that in interactions between light and atoms, the momentum is transferred in a direction only determined by chance. I stress this because most popular accounts insist that Einstein could not accept the probabilistic nature of quantum physics. The truth is that Einstein was fine with probabilities. In fact, he introduced them and used them all the time. The real problem that Einstein had in the late 1920s with quantum mechanics was that despite its success, it appeared as an incomplete theory about the underlying physical phenomena. Since his proposal of the light quanta hypothesis in early 1905, Einstein had been careful on referring to light not as particles, and only used light quanta instead. During the years, he even searched for ways to avoid light quanta altogether, and only used light waves, but he found inconsistencies in the form of violations to the conservation of energy. The results reported in this article finally convinced him that light particles were real. In a follow-up letter to Bessel in September 1916, Einstein wrote, "The result obtained is that at each elementary transfer of energy between radiation and matter, the impulse quantity, hν over c, is passed on to the molecule. Thus light quanta are as good as established." He later wrote, "I no longer have doubts about the reality of quanta in radiation, even though I am still quite alone in this conviction." He stressed the word reality in his letter, and in fact it took several more years until 1923 for Compton's study of X-ray scattering for Einstein's light particles to be widely accepted. After the formal development of quantum mechanics, in early 1927, Paul Dirac published an article titled "The Quantum Theory of the Emission and Absorption of Radiation." In this paper, Dirac included a section in which he systematically calculated the Einstein coefficients using the newly formulated quantum mechanics. In this old notation, Dirac's calculation is quite hard to follow, but today, this is an exercise that every undergraduate student has to do at least once in a quantum mechanics course. I remember doing this as a homework assignment many years ago, but I was not taught its significance. In modern notation, Dirac found these results, where the strange-looking object on the right represents a matrix. Don't worry if you are not familiar with this notation. In simple words, this object is a matrix that represents the probability of an atomic transition between the states J and K. Once we have these explicit expressions, there is one more thing to do. Take the ratio between A and B. After simplifying a bit, we get this quantity. If I bring back an earlier result, we find how Dirac confirmed that Einstein's guess was correct. In the final section of his paper, Dirac wrote, "We shall now show that the Hamiltonian leads to the correct expressions for Einstein's A's and B's," and ended the summary with a humble but quite powerful line. "The theory leads to the correct expressions for Einstein's A's and B's." During the early 1920s, Einstein's A and B coefficients served as the guiding principle in the description of absorption, emission, and one of the most fascinating phenomena in optics, dispersion. It is the study of this process, guided by Einstein's coefficients, that led some less-known names like Rudolf Ladenburg, John Slater, and Henry Kramers to lay the foundations for Heisenberg's groundbreaking theory that became known as matrix mechanics. Einstein's intuition led him to predict a completely new way for atoms and light to exchange energy, which he used to establish a deep connection between Planck's black body radiation and Bohr's atomic model. Next time that you scan an item in a store, remember that all started with a thought of light and atoms in a box.